Insertion. So we'll discuss the insertion operation part of binary search algorithm. We'll say we want to insert the 45 to our example 3. The first thing we'd have to do is find the correct node to attach the 45 to. To begin our search, we start at the root node. So we start here 50. So since binary search tree follow a certain or structure, data structure in which the left child needs to be less than the parent. Therefore, before we insert something, we need to perform search operation. Just like in an ordered array, for inserting it in the middle of the ordered array, we need to search first where we would have to insert it to keep it in order. So here, we begin our search at the root node. Since 45 is less than 50, we drill down to the left child, which is 25. Since 45 is greater than 25, we must inspect the right child. Since 45 is greater than 33, we check the 33's right child. At this point, we've reached a node that has no children, so we have nowhere to go. This means we're ready to perform our insertions. Since 45 is greater than 40, we insert it as the right child of the 40. In this example, insertion took 5 steps. So here, it actually took 5 steps since we searched that 4 times, the value for 4 times. First here, we compare that with left and right child, and then 25 second, we compare that 10 and 33. And then in 33, we compare with 30 and 4 with the value that we want to insert, and we get to 40. Once we get to that 40, we insert the 45, which makes it 5 steps, consisting of 4 search steps plus 1 insertion steps. Insertion always takes just one extra. Let me just zoom out. Just take just one extra step beyond the search, which means insertion takes log n plus 1 steps. So in big O, we disregard that plus 1. In ordered array, by contrast, insertion takes on, because in addition to search, we must shift a lot of data to the right to make room for the value we're inserting. So again, in ordered array, by contrast, insertion takes on, because in addition to search, in searching all the values, we must shift a lot of data to the right to make room for the value we're inserting. Since it's an array, we need to shift it to the right, if we're inserting at the middle. So here's a Python implementation of this binary search tree. So like the search function, it's recursive. Like the search function we discussed in the previous video, it's also recursive. So we define insert with the argument value and node. So the insert function value that we're going to the insert function accept a value that we're going to insert. So this value is the one we're going to insert, and a node that serves as the ancestor node for which our value our value will become a descendant. So notice how we're inserting it not in an index, unlike the insertion we performed before. We're trying to insert at a certain index in an array. Here, we're just trying to define the ancestor where our node, our search will start. So in this case, which our value will become a descendant, because the value basically would become less than this ancestor. So that's one of the criteria of our insertion algorithm. Now first, we check whether the value is less than the value of the current node. So this is the checking or that application of that criteria. We check whether the value is less than the value of the current node. So if value is less than node.value, therefore, if the value is less than the node, we know that we need to insert the value, something among the left descendants of the node. Uh, we then check to see whether the current node has a left child. If the node doesn't have a left child, we make the value into the left child. So let's say we're now define the node value as less than 8. We know that if we recursively call this left child, we will eventually get to the value that we're looking for. Now, we know that if that doesn't have a left child, meaning that we stop on the value that we can keep recursively searching, or basically we define or we now found where we should insert the value which is on the left child. So since that's exactly the value belong, we create this code. If node that left child is none, node that left child equals to 3 node value. So we add the value on that node. So we make the value into the left child. So since that node does not have any left child, we can't recursively call that here. So if value is less than node dot value, if node dot left child is none, node dot left child equals to 3 node. So else we will insert or recursively the value with the arguments value and node dot left child. So this is the base case. We don't need to take any recursive calls. So this is what will happen if the root node doesn't have a left child, or the left child of the root node doesn't have a left child anymore. However, if node already has a left child, we can place the value there instead. Since we're not overwriting, okay, unlike the other operation that we had performed before, and we will perform moving we we will also perform moving forward. We need to have a base case. So notice in this case, the recursive call or this recursive function has a base case as well. Now this is the base case. However, if node already has a left child, we can place the value there because we're not overwriting. Instead, we recursively call insert on the left child, so that we continue to search for the spot in which we'll place the value. So if the node already has left child, we can place the value there. Right, so we cannot place because we're not overwriting. Then we recursively call insert on the left child. So here, as you can see, insert and then the value node that left child. This is how we recursively traverse that left child, so that we can continue to search for the spot in which we'll place the value here. So that's this code means. Else insert, so that we can continue to search for the spot in which we'll place the value. Eventually, we'll hit a descendant node that doesn't have its own child, and that's when the value is going to go. So we will return to this base case. The rest of the function is the exact inverse. It handles the cases where the value is greater than the current code. So here, if it's greater than, so it's kind of like the same. If right child is none, so insertion is kind of easy to understand, which is really easy compared to deletion, which we're gonna discuss later. So it's important to note that only when creating a tree out of randomly sorted data do trees usually wind up being well balanced. So if the data is already ordered, it will not be balanced anymore, as you can see here. So whenever you're gonna use insertion or binary search tree insertion operation, you need to make sure that your data is randomly sorted. So however, if we insert sorted data into a tree, it can become imbalanced and less efficient. For example, if we were to try to insert the following data in this order, so it will become imbalanced. So it's the opposite here. You may think that having the uh, data in order, just like in an array, will also make the searching or insertion rather efficient in node data structure such as binary search. It's actually incorrect. So this tree is completely linear. So searching for the 5 within this tree would take on. However, if we inserted the same data in the following order, such as this, the tree would evenly balance now. So because of this, if you ever want to convert an array into a binary search tree, you'd better first randomize the order of data. It emerges that in a worst case scenario, when a tree is completely imbalanced, search is on. In a best case scenario, when it's perfectly balanced, search is O log n. So the fast or the time complexity or how fast it is actually depends on how balanced the tree is. So if it's perfectly balanced in which data is inserted, so it's kind of like opposite of an ordered array, right? Or of what we intuitively think as an ordered, because for trees, a random order is actually the what it calls balance. So a tree will be pretty well balanced and search will take about O log n, and therefore it can optimize its insertion operations. So here, deletion. So let's say we want to delete 4 from this binary search tree. So here, first we perform a search to find the 4. So we also perform a search just like insertion. We won't visualize this search again since we've already got that down. Once we find the 4, we can delete it in one step. So well, that was simple. So that's a simple part of this algorithm. But let's see what happens when we try to delete the 10. So if we try to delete it, we'd end up with an 11 that isn't connected to the tree anymore. And we can't have that in a well-balanced or binary search tree, because a binary search tree has a characteristics in which it has to be balanced. Now, because if we let that happen, like we delete that, we'd end up with 11 and we'll lose that forever. Remember, our node data structure just put the node or that data in the computer, and the programming language somehow make way to delete that in the backend, but we won't be able to access that data anymore. However, this is a solution to this problem. We can plug the 11 into where the 10 used to be. So far, our deletion algorithm follow these rules. If the node being deleted has no children, simply delete it, which is the simplest case. If the node being deleted has one child, delete the node and plug the child into the spot where the deleted node was. So we're plugging the child, so we're transferring it, we're not overriding it. So that's a key concept. So here, deleting a node sorry about that. So let's discuss the case where we're deleting a node with 2 children, which is the most complex. So deleting a node that has 2 children is the most complex scenario. Let's say we want to delete the 56 in this tree. So what are we going to do with its former children, 52 and 61? We cannot move both of them to where the 56 was. Right? So this is where the next rule of the deletion algorithm comes into play. When deleting a node with 2 children, replace the deleted node with the successor node. So if we're deleting that a node with 2 children, we need to replace the deleted node with the successor node. So later we will discuss what the successor node in these 2 children. So the successor node is the child node whose value is the least. Okay, whose value is the least of all values that are greater than the deleted node. So what is the least value here? That also, so it's a tricky question, right? So the successor node is the child node whose value is the least of all values that are greater than deleted node. So what is the values that are greater here than the deleted node? It's 61. Also, that's the least values here of the parent node, which is 75, right? That would be your replacement value. Now, that was tricky sentence. To put it in other words, if we were to put the deleted node and all of its descendants in ascending order, the successor node would be the next number after the one just deleted. In this case, it's easy to figure out which node is the successor, since the deleted node had only 2 descendants. If we put the numbers 52, 56, 61 in ascending order, the next number after 56 is 61. Once we find the successor node, we plug it into where the deleted node was. So we replace the 56 with 61. Now, how does the computer find the successor node? So this can be tricky when we delete node high up in the tree. So here's the algorithm for finding the successor node. Visit the right child of the deleted value and then keep on visiting the left child of each subsequent child until there are no more left children. So the bottom value is the successor node. So in this case, we deleted what we deleted. So 56. So what the algorithm means is that we need to visit the right child first. Here, visit the right child of the deleted value, and then keep on visiting left child of each subsequent child. So we need to keep visiting the left child of the subsequent child of that 61. However, there's no left, so the bottom value is the successor node. So therefore, that bottom value, the 61, is the successor. So what if we deleted a root node in this case? So let's see this again in action in a more complex example. Let's delete the root node. So we now need to plug the successor node into where the 50 was and turn it into the root node. So let's find the successor node. So to do this, we visit the right child of the deleted node and then keep descending leftward until we reach a node that doesn't have left child. So here we pull the right child first, and then we keep visiting the left child until we reach a node that doesn't have a left child. So until we reach that node that doesn't have a left child. In the previous example, that's 61. Now it's 52. So it turns out that 52 is the successor node. Now we found the successor node, we plug into the node we deleted, and we're done. So successor with right child. However, there's one case we haven't accounted yet. And that's where the successor node has a right child of its own. Let's create the preceding tree. So what if the successor node, like this, has a right child of its own? How do we find the how do we handle that case? So let's create the preceding tree, but add the right child to the 52 as shown in the diagram on the next section. So however, there is one case we haven't accounted for yet, and that's where the successor node has a right child of its own. Let's create the preceding tree, but a right child to the 52 as shown in the diagram on the next section. So again, however, there is one case we haven't accounted for yet, and that's where the successor node has right child of its own. So I have to delete that because that's a tricky sentence as well. Let's create the preceding tree, but add the right child into the 52 as shown in this diagram. In this case, we can simply plug the successor node. We can simply plug this because we will be left with 55 and we lose that data forever into the root since we'll leave its child of 55 hanging. Because of this, there's one more rule to our deletion algorithm. If our successor node has a right child, after flagging the successor node into the spot of the deleted node, so we know that once we get to this successor node, there is no more left child because this is actually a left child, or the base case, or the base where we left the left child. It can only have this right child. So in this case, if the successor node has a right child, after plugging the successor node into the spot of the deleted node, so after plugging the successor node into the spot of the deleted node, take the former right child of the successor node and turn it into the left child of the former parent of the successor node. So we turn that as a left child of the former parent of the successor node, which is the 61. So that was another tricky sentence. So let's walk through the step. First, we plug the 52 into the root. This leaves the 55 dangling without a parent. Now we simply plug that to the as a left child of 61. Next, we turn the 55 into the left child of the former parent of the successor node. In this case, 61 used to be the parent of the successor node. So we make the 55 the left child of the 61. And now we're really done. So these are the complete deletion algorithm. If the node being deleted has no children, simply delete it. If the node being deleted has one child, delete the node and plug the child into the spot where the deleted node was. When deleted a node with two children, replace the deleted node with the successor node. The successor node is the child node whose value is the least of all values that are greater than the deleted node. And then, to find the successor node, visit the right child of the deleted value and then keep on visiting the left child each subsequent child until there are no more left children. The bottom value is the successor node. And then, if the successor node has right child, after plugging the successor node into the spot of the deleted node, take the former right child of the successor node and turn it into the left child of the former parent of the successor node. So here's a Python implementation for a binary search tree. Let's see this in action. Deletion algorithm. So first we define a delete, simply delete, and then an argument value to delete node, value to delete and node. So the base case is when we've hit the bottom of the tree and the parent node has no children. So let's say we're trying to delete something, the parent node has no children. So that's the base case, that's the easiest case. So if node is none, return none. So if the value we're deleting is less or greater than the current node, we set the left or right child respectively to be the return value of recursive call of this very method on the current node's left or right subtree. Again, I'll repeat it. If the value we're deleting is less or greater than the current node, we set the left or right child respectively to be the return value of recursive call of this very method on the current node's left or right subtree. So here, else if, so that's the first if, else if value to delete is less than node.value, node.left child equal delete, value to delete node.left child. And then we return the node. We return the current node and its subtree if existent to be used as the new value of its parent's left or right child. So that's a tricky one. Remember, this is the one of the most complex part of this course. So admittedly, this code is a bit involved. So let's break down a bit. Let's start before we move on to the next if-else code. Um, or if. So basically, first we define delete function, right? So the value to delete is the value we're deleting from the tree, and the node is the root of the tree. So the node, the here is actually the root, the same, the same parameter that we're using for binary search tree is actually the argument is the root of the tree. So when we first call this function, the node will be the actual root node. But as this function call itself recursively, the node may be lower down in the tree and simply be the root of a smaller subtree. So as we call it recursively, this node will change. It may become just a parent node of a subtree. In any case, the node is the root of either the whole tree or one of its subtrees. So it's the node is the root of either the whole tree. So it's not the whole tree because it's changing as the recursive function calls itself. The base case is when the node does not actually exist. So if the node does not exist, like if it's not an ancestor, so that's the base case. That's the simplest case where we just simply delete it because there's no children. Now this will happen when a recursive call to this function tries to access a child node that does not exist. In this case, we return none. So this is the base case. Next, we check whether the value to delete is less than or greater than the value of the current node. So this is the next of the base case. Now, we're gonna discuss this further or in more details. So we're gonna repeat this because this is the start of the more complex code later. So we will check whether the value to delete is less than or greater than the value of this current node. So initially, this is the root node of the tree. So if value to delete is less than node.value, node.leftChild equals to delete, value to delete, node.leftChild, return node. So that's what this code means, where we left off. If value to delete is greater than, so basically we came from the root node and we examine if it's a left or right node. Then we're gonna recursively call that. So that's where this is. So and then we'll move on to this next code. We'll back on this Python code. So if value to delete is equals to node.value. So if the current node is the one we want to delete, right? We've done with the search and then we got the value we want to delete. Now if the current node has no left children, so we can simply just delete it. We need to now implement those cases we've determined in our pseudocode. Now if the current node has no left child, we delete it by returning its right child. Sorry about that. So if the current node has no left child, so it's only have right child, we delete it by returning its right child. So in its subtree if existent to be its parent's new subtree. So it will become, if node.left child is none, return node.right child. So this is the last example where we have a 55. Sorry about this. Where is that? Here, new right child. So successor node with a right child. So once we delete this, if it's no left child, we replace this 55 to be the new subtree of this parent 61. So that's what that code means, the first code. So again, let's go back to this again. As I said that I will gonna emphasize this this snippet may not be immediately intuitive, but here's how it works. If the value to delete is less than the value of the current node, we know that if the value to delete is to be found somewhere in the tree, it will be found among the current node left descendants. So if it will be found anywhere in the tree, it will be found on the left descendants because of the structure of the tree. Here's the clever fight. We then overwrite the current node left child to be the result of recursively calling the delete function on the current node left child. Again, we then overwrite the current node left child. So the current node left child, we're gonna override it to be the result of recursively calling the delete function on the current node left child. So we are recursively calling the delete function on the current node left child. Remember, the current node changed as we progressed on the tree. So since we already know that it is less than, or it is the left child, we recursively call that left child. Now value to delete comma node that left child, and then we return the node. So the delete function itself eventually returns a node. So eventually it will return a node. So we take this result and make it the current node's left child. So we return a node. So eventually we make this as the current node left child. So often, however, this overlay doesn't actually change the left child, because calling delete on the left child may return that same left child. So it may not actually, this overlay doesn't actually change the left child, because calling delete on the left child may return that same left child. So to make sense of this, imagine we're trying to delete 4 from the example of this. Originally, the node is the root node, which is the value of 50. Since 4, the value to delete is less than 50, we'd say that 50 left child should now be the result of calling the delete on the 50's current left child, which is 25. So what will be 50's left child be? So let's see. When we recursively call delete on 25, we begin we again determine that 4 is less than 25, the current node. So the 25 is actually the current node while we're recurring that recursive delete function. So we continue the recursion with the 25's left child, since this value does not equal to the node value to delete. So this is what this means. Value to delete, comma node left child. We're comparing that, which is the 10. However, no matter what's the left child will end up being, since we say return node, we return the 25 node at the end of the current function call. This means that back when I said that 50's left child should be the result of calling the delete on the 25, we ended getting back the 25 itself. So the 50's left child actually remains unchanged. The current node's left or right child will change, however, if the result of the next recursive calls involves an actual deletion. So let's examine that bit of code next. So elif value to delete is equals to node.value. So if we find the node.value equals to, here the node.value is equals to so that's the key. The node.value is one of the things that we want to emphasize, because as you can see, we created the base case and we create the less than and then greater than code, and if value to delete is equals to node that value, that's where we will perform depending on different edge cases or scenarios belong to that code. So let's examine that further. Now here, the current node's left child of the right child will change. However, if the result of the next recursive call involves an actual deletion, let's examine the bit of the code. This is to say, the current node is the one we want to delete. In order to delete it properly, we first need to determine whether the current code has any children. So again, if the current code is the one we want to delete, therefore we need to think of the edge case, such as if it has a right child or if it has two children, which is the most complex. Whether the current code has any children still affect the deletion algorithm. We begin by checking whether the node we're going to delete has any left children. So if the current node has no left children, so this is the successor node with right child, we can return the current node right child as a result of this function. So as a result of this function, we can return the right child. Remember, whichever node we return will become either the left or right child of the previous node. So in this case, since we've gone to this code, part of the code or section of the code, remember that whichever node we return will become either the left or right child of the previous node in the call stack. So again, this is a stack again with the like the stack queue, because we're calling it recursively. So whatever we return here will be the child of the previous parent we just called. So let's imagine the current node has a right child. In this case, by returning the right child, we make it a child node of the previous node in the call stack, effectively deleting the current node from the tree, and then what do you call this? Plugging this new return value, which is node that right child. Now, if the current codes happen to have a right child, that's okay too. So since we'll end up passing none as a result of this function. So here, so if node that right child is none, return node that left child. So this is the case where in which, like, let's see, we don't have a right child, so we only have left child. We will return to, so now if the current code node happens to have a right child, that's okay too, since we'll end up passing none as a result of this function, and that will also effectively remove the current node from the tree, and that will also effectively remove the current node from the tree. Moving on in our code, if the current nodes does have a left child but doesn't have a right child, we can still easily delete the current node. So as you can see, guys, it's a bit more complex to explain this, but let's go back and compare this with the tree or the graph, because that's a better representation of this. So here we got this edge case in which we are we're deleting as a node with the right child. So we're just finding where. Here, I think this is the successor node, 52, no. So if the node being deleted has one child, delete the node and plug the child into the spot where the deleted node was. So I think this is that case. Yes, so if there's a one child, I see. So here, since there's only one child here, I think that's not the left child anymore. So this is the two children. I think this, yeah. No. So let's just examine the code. Here we're hanging a 55. Let's just examine the code. So now if the current node happens to not have a right child, that's okay too. So if though that right child is none, that's okay, since we'll end up passing none as a result of this function. So if it doesn't have a right child and we recurse it to the left, right, if value to delete, so it doesn't have a right child, right? And then we will not replace that node, since we'll not we're not gonna return the right child, we're gonna return the node that left child. Sorry, this case is actually where when there's no two children, right? So usually if there's two children, we return the one that is greater than the children, so that's usually the right child. Now if there's no right child, we return node that left child, of course, to pass that as the replacement of that as a children. So now if the current node has not happens to not have a right child, that's okay too, since we'll end up passing none as a result of this function. And that will also effectively remove the current node from the tree. Moving on in our code, if the current code does have a left children, and doesn't have a right child, we can still easily delete the current node. In this case, we delete the current node by returning its left child to become the child node of the previous node in the call stack. So that node that left child will become the child node of the previous parent node of the one we deleted. So let's say if the node doesn't have a left or right child, then we simply delete the node. So that's actually the base case. So here, we're done here. Now, if the current node has two children, we delete the current node by calling the leaf function below, which changes the current node value to the value of its successor node. So if there's a two children, this is the most complex because we call the leaf node. So if the current node has two, we delete the current node by calling the leaf function. So this is how we delete it, using a leaf function, which is below, which changes the current node value to the value of its successor node. So we use a successor node, which is leaf node and then node to delete. If node that left child equals to leaf node that left child node to delete, return node. Else node to delete that value equals to node that value, then return node that right child. So if it's a left child, so this is actually the case where we return the right child. Now let's examine this further. So finally, we encounter the most complex case in which the node we're deleting has two children. Now else node that right child equals to leaf node that right child node, then return node. So in this case, we call the leaf function, take its result and make it the current node's right child. So since we have the we call the leaf function and take its result. We delete that and then take its result and make it the current node's right child. So what does leaf function do? When we call it, we pass the current node right child in addition to the node itself. The leaf function accomplished four things. It finds the successor node, it overwrites the value of node to delete and makes it the value of the successor node. This is how we get the successor node into the correct spot. Note that we don't move the actual successor node object anywhere. We simply copy its value into the node we're deleting. So to eliminate the original successor node object, the function then turns the original successor node's right child into its parent's left child. So the function turns the original successor node right child. So this is where the right child, we replace the actual node when it's two children. So this is simply what that means. So after all the recursion is said and done, it finally returns the original right child passed into the first place. So it's usually the right child that passed on in the first place, or none if the original right child. So we then take return value of leaf and make the current node's right child. This would either leave the right child alone or change it to none if the right child was used as the successor node. So it's pretty complex. So it really takes time to learn this part, but after that, it becomes easy. The other algorithms for this code and other data structures as well. So like search and insertion, deleting from trees is also typically OLAG, and this is because deletion requires a search plus a few extra steps to deal with any hanging children. Contrast this with deleting a value from an ordered array, which is ON, due to shifting elements to the left to close the gap of the deleted value. So it's OLAG N, since we don't need, because it only requires a search plus few extra steps rather than shifting all values to the left. So if we're inserting, we're shifting values to the right in an ordered array, right? So binary search trees in action. We've seen that binary search trees boast efficiencies of OLAG N for search, insertion, and deletion, making it an efficient choice for scenarios in which we need to store and manipulate ordered data. This is particularly true if we will be modifying the data often. So for modifying data often, such as searching and deleting, it's often better to use this binary search algorithm compared to ordered array, because it has an OLAG N insertion and deletion, in which we need for application in which we need to store and manipulate ordered data. So again, it's about ordered data, binary search tree. Notice the similarities of this in binary search algorithm, in which it's also used in unordered. So whenever we're talking about binary search or binary anything binary search, we're talking about assorted data or unordered data. Now this is particularly true if you will be modifying the data often, because while ordered array are just as fast as binary search trees when searching data, binary search trees are significantly faster when it comes to inserting and deleting data. For example, let's say we're creating an application that maintains a list of book titles. We'd want our application to have the following functionality. Our program should be able to print the list of book titles in alphabetical order. Our program should allow for constant changes to the list. Our program should allow for the user to search for a title within a list. So it's allow for search, like a search, a search text box, and it's allow for print the list of books in alphabetical order. So to list all that in alphabetical order, and for constant changes to the list. Let's say we add another book, since there's a lot of books in the world, so we often have to insert, delete, etc. Now, if we didn't anticipate that our list would be changing that often, an ordered array would be suitable data structure to contain our data. However, we're building an app that should be able to handle many changes in real time. If our list had millions of titles, a binary search tree may be a better choice. Such a tree might look something like this. So here, the titles are positioned on their alphabetical order. A title that comes earlier in the alphabet is considered a lower value, while titles that come later are greater values. So here are the A. You can think of this as lesser value than the root value. So Alice, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, B, R, M, N, O, P. This is P, Q, R, S, T. So here, the titles are positioned based on their alphabetical order. A title that comes earlier in the alphabet is considered a lower value. Right? So, binary search tree traversal. So, how do we print the list of the book titles in alphabetical order? So, this is the nitty-gritty question. So, first, how do we actually print that list with on our app like Shopee? How does it provides the list in ascending order or alphabetical order or based on price? Now, first, we need the ability to visit every single node in the tree. So we need an ability to visit that, to traverse all of it. Visiting node is just another term for accessing them. So visiting it is just another form of accessing it. So you may imagine how we will apply that in our code. So the process of visiting every node in a data structure is known as traversing data structure. Second, we need to make sure we traverse the tree in alphabetically ascending order so that we print the list in that order. So since we know that all the left are the first, we will traverse if we're starting from A, and all the right will traverse if we're starting from Z. So therefore, we'll start with this when traversing or when printing the list. So this is actually how it works in details. So there are multiple ways to traverse a tree, but for this application, we will perform what is known as in-order traversal so that we can print each title in alphabetical order. So again, in-order traversal. There are other ways to traverse a tree, but here we're using in-order traversal. Recursion is a great tool for performing traversal. We'll create a recursive function called traverse that can be called on a particular node. So recursion is actually a great tool for performing traversal. So whenever we're printing a list, we're actually using recursion beneath it or under hooded. So we'll create a recursive function called traverse that can be called on a particular node. So in this algorithm, we'll create a recursive function that can be called on a particular node in this tree. The function then performs the following steps. Call itself traverse recursively on the node's left child. So it will call traversedly in the node's left child. In this case, in this left child of Moby Dick. So the function will keep getting called until we hit a node that does not have a left child. So here, it means that this is the lowest in this binary search tree. Visit the node for our book title app. We print the value of the node at this step. So visit the node, like accessing it in the algorithm. Call itself again, traverse recursively on the node's right child. The function will keep getting called until we hit a node that does not have a right child. So we visit the node once we get to the most left child, and then we call our also itself recursively on the node's right child until we get it in alphabetical order. So here is the application of that. For this recursive algorithm, the base case is when we call traverse on a child that does not actually exist, in which case we return without anything further. So in this algorithm, we're handling the case in which we traverse on a child that does not actually exist, or doesn't have doesn't have a node or value, in which case we return without any doing any further. Here's a Python traverse and underscore print function that works for our list of book titles. Note how concise it is. We def traverse underscore and underscore print with the argument node, and then colon. If node is none, we return. If and then after that, traverse underscore and underscore print node dot left child, print node dot value, and traverse underscore and underscore print node dot right child. So it's so concise, unlike the delete algorithm, right? So we first call traverse and print on Moby Dick. This in turn calls traverse and print on the left child of Moby Dick, which is Great Expectation. Before we move on to that, though, we're going to add to the call stack the fact that we're in the middle of the function in Moby Dick. So before we move on to that, we're going to add to the call stack. So again, it's recursive, it's still in the stock. We're going to add to the call stack that we're in the middle of the function in Moby Dick, and the fact that we're in the middle of traversing its left child. So here, Moby Dick colon left child. We then proceed traverse and print Great Expectations, which is the next in this binary tree. Here, the left child. So as you can see, it works like a stock in which we start with the root node, and then we enter the next node, and then the next node, and then the last node will eventually the first or the alphabetically. So this is how we print that ascending or alphabetical order in binary search tree. So this is how it practically applied in the real world. So let's see it in action now. So the traverse, so let's add traverse and print Great Expectation to the call before moving on. The traverse and print Alice in Wonderland calls traverse and print on the left child of Alice in Wonderland. So now we hit the very bottom of left child. However, there isn't any left child, the base case, so nothing happens. The next offline of traverse and print is print node.value, which prints Alice in Wonderland. Next, the function attempts to traverse and print the right child of Alice in Wonderland. So after that, it will traverse that, which is the next alphabetically, which is the Lord of the Flies, right? A, B, C, D, E, F, G, H, I, J, K, L. No, it should be Great Expectation, but it just put that Lord of the Flies in the stack. So calls traverse on the left child. However, there's indecent. So here next, the function attempts to traverse and print the right child of Alice in Wonderland. So traverse and print know that right child. However, there's no right child, the base case. So the function returns without doing anything further. Since we completed the function traverse and print Alice in Wonderland, we check the call stack. So however, there's no right child. There's no right child in Alice in Wonderland. So the function returns without doing anything further. Since we've completed the traverse and print Alice Wonderland, we check the call stack to see we're up to in this recursive soup. So that's right, we're in the middle of traverse and print of Great Expectation recursive call, and we had just completed calling traverse and print on its left child. So let's pop this from the stack. So we print, let's continue. The function next prints Great Expectation and then calls traverse and print on the right child, which is the Lord of the Flies. So before moving on to that though, let's hold our place within this function in the call stack. So here's what it looks like. We now execute traverse and print Lord of the Flies. So we execute the Lord of the Flies. First, we call traverse and print on its left child, but it doesn't have one. Next, we print Lord of the Flies. Finally, we call traverse and print on its right child, but that doesn't exist either, so the function is now done. We look at our call stack and see that we're in the process of executing traverse and print on the right child of Great Expectation, we can pop that from the stock and continue as shown in the diagram. So we pop out the Great Expectation after Lord of the Flies, A, B, C, D, E, F, G. Now it just happened that we've also now completed everything that we have to do in traverse and print Great Expectation. So we can go back to the call stock to see what to do next. So we can see that we're in the middle of traverse and print of the left child of Moby Dick. We can then pop that from the call stock, which leaves the stock empty for now, and continue with the next step within traverse and print Moby Dick, which is to print Moby Dick. Then we call the traverse and print on the right child of Moby Dick. We'll add this to the call stock. So here, first, the sake of brevity, although it's probably too late for that, I'll let you walk through the rest of the traverse and print function from there. By the time our function has finished executing, which one of the characteristics of recursive function is we don't need to know the details in that recursive function. We just know that it will turn it in proper order. So we discussed this. As you can see, we have a small code there. Without this representation, we wouldn't be able to understand how the code works in its detail, on its bits and data, right? So here's how it works. First, we call Alice in Wonderland, then Great Expectation, then Lord of the Flies, then Moby Dick. Then after that, it will call it recursively until we get to the left. And then 5, we get the 5, and then we go back, we call this Robinson Crusoe, and then the last, the Odyssey. And now, that's how we achieve our goal of printing book titles in alphabetical order. Note that traversal is ON, since by definition, traversal visit all nodes of the tree. So the binary search tree is powerful node based. So this traversal or printing is actually ON, but it makes it ON, that's the best that we can do, since we have to actually print all the list. So the binary search tree is a powerful node-based data structure that provides order maintenance, while also offering fast search, insertion, and deletion. It's more complex than its linked list cousin, but it offers tremendous values. So keeping your priorities straight with heaps. So in this chapter, we'll explore the heap. So a type of data structure that has special powers that can be leveraged for specific scenarios. So in particular, when we want to constantly keep tabs on the greatest or least data element in a data set. To appreciate what a heap can do, let's take a look at a completely different data structure, the priority queue. So a heap is a type of tree data structure again, but it has a special power in specific scenario, in which case to name it is a priority queue. So remember, priority queue means that data is inserted only at the end of the queue, and also it's an abstract data type, right? So end of the queue meaning the end of the index if it's an array. But here, let's see, we're gonna use an array as well, but we're gonna use a heap structure, and data is accessed and removed from the front of the queue. So for priority queue, the front is at the end of the index of the array, and it is accessed and removed from the front, which is at the end of an array. In accessing the queue's data, we give precedence to the order in which the data was inserted. So a priority queue is a list whose deletions and access are just like a classic queue, but whose insertion are like an ordered array. So for in accessing queues data, we give precedence to order in which the data was inserted. Since we can only access the end, and we're trying to have it in queue, we can only insert at the beginning. So remember, in ordered array, if we're inserting at the beginning, we have to shift everything to the right. So one classic whose deletion and access are just like a classic queue, but whose insertion are like an ordered array. So this is how priority queue works. That is, we discussed this in the previous video. the priority queue, and we applied it to an array as well, an ordered array. Now, that is, we only delete. So notice guys, this priority queue use is a kind of like a data structure, uh, but it uses an ordered arrays in it, under hood. So it's on top of ordered array. So ordered arrays, those are the most basic concepts, but the priority queue use that under the hood. Now we're gonna change that ordered array implementation into a heap structure. So we were gonna explain what heap is sooner. So that is, we only delete and access data from front of the queue, but when we insert data, we also always make sure that data remains sorted in a specific order. One classic example of where priority is helpful is an application that manages triage system for a hospital room. In the ER, we don't treat people strictly in the order in which they are arrived. Instead, we treat people in the order of the severity of their symptoms. If someone suddenly arrives with a life-threatening injury, that patient will be placed at the front of the queue. So we discussed this in the previous video, but it's the same concept here. Like for heap, we can use, instead of ordered arrays that has an ON insertion, we can use a heap to make it O log n insertion, so that we optimize that. We really optimize that in this scenario of triage room. So again, we place that in front of the queue based on the priority. Even the person with the flu had arrived hours later. Let's say our triage system is ranked the severity of patient's condition on a scale of 1 to 10, with 10 being the most critical. Our priority queue may look like this. So even though patient A arrived earlier, but the severity is not that high, therefore it's not the priority. So in determining the next, so there's two variables that you need to determine, the time as well as the severity. In determining the next patient to treat, we will always select the patient at the front of the queue, since that person's need is the most urgent. In this case, the next patient we treat is patient C. If a new patient now arrives with a condition of severity 3, we'll eventually place this patient at the appropriate spot within the priority queue. We'll call this patient E. So before, this insertion takes ON because we need to ship the array or the array to the right. So the priority queue is an example of an abstract data type. That is, it can be implemented using other more fundamental data structures. One straightforward we can implement a priority queue is by using an ordered array. That is, we use an array and apply the following constraints. When we insert data, we ensure we always maintain proper order or shifting all to the right. Data can only be removed from the end of the array. This will represent the front of the priority queue. The priority queue has two primary operations, deletions and insertions, which a heap is optimized for. We've seen in why data structures matter that deleting from the front of the array is ON, since we have to ship all the data over to fill the gap created at index 0. However, we have cleverly tweaked our implementation so that we consider the end of the array to be the front of the priority queue. So remember guys, it's just an ordered array under the hood for our classic priority queue. But we can use a heap array as well, right? So in this video we will gonna discuss how we can use heap array under the hood of priority queue. So this way, we're always deleting from the end of the array, which is O1. With O1 deletions, our priority queue is in a good shape so far. But how about insertion? Since these are optimized for insertion, so this structure or problem are optimized for constant insertion and deletion, we also want to optimize insertion. So the way to optimize insertion is to actually use a heap array under the hood. So you learn that inserting into an ordered array is O(n), since we have to inspect up to all n elements of the array to determine where our new data should go. And even if we find the correct spot early, we need to then ship all the remaining data over to the right. And even if the search is fast, we also need to ship the array to the right, since it needs to be ordered. Our array-based priority queue then has deletion that are O1 and insertion that are O(n). If we expect there to be many items in our priority queue, the O(n) insertion may cause some real unwanted drag in our application. Because of this, computer scientists discovered another data structure, or heap array, that serve as more efficient foundation for priority queues. So heaps. There are several different types of heaps, but we're going to focus on the binary heap. Now, even binary heap come into two flavors, the max heap and the min heap. In this video, we're gonna discuss mainly the max heap, but basically they have the same idea, in which for max heap, all of its descendants are less than it, and then for min heap, all of its descendants are greater than it. So, but as you'll later see later, the difference between the two is trivial. Going forward, I'm going to refer to this structure as simply as heap, even though we're specifically working with the binary max heap. So the heap is a binary tree that maintains the following condition. So heap is so what is heap? Array, you may ask. Heap is a binary tree as well. It's a form of binary tree, but it is an array. It's not a node data structure, in which it maintains this condition. The value of each node must be greater than each of its descendant nodes, which is the max heap. This rule is known as the heap condition. The tree must be complete, so I'll explain this shortly. The condition says that each node value must be greater than each and every one of its descendants. For example, the following tree meets the heap condition since each node is greater than any of its descendants, as shown in the diagram. So the following isn't a valid heap because it doesn't meet the heap condition. Here, 92, which the children or the child is greater than its parents. So ultimately, whether a heap is max heap or min heap is pretty trivial. Everything else is about heaps is identical. They only have reverse heap conditions. Otherwise, the fundamental idea is the same. So a complete heap is a tree that is completely filled with nodes. No nodes are missing. So if you read each level of the tree, left to right, all of the nodes are there. So this is what the complete node means, or one of the conditions to say that it is a binary heap. So however, the bottom row can have empty position as long as there aren't any nodes to the right of this empty position. This is best demonstrated with this example. So one of the things that condition that needs to be satisfied is it needs to be complete. So what do you mean to be complete? It means that as long as there are any nodes to the right of these empty positions, so these as long as there is no nodes to the right of this empty position, these are the graph for that. As you can see, there's no node on this empty position, so it's said to be complete. So the following tree is complete since each level, meaning each row of the tree, is complete, filled in with nodes. The following tree is not complete since it's missing a node on the third level. It's missing the node on the third level, which is the right node. Now, the tree is actually considered complete here, since its empty position are limited to the bottom row, and there aren't any nodes found to the right of the empty positions. So as you can see, what's the difference of this node and this node? This node is from the left, it's not from the right. So it needs to be at the right of the ancestor. So now the next is actually considered complete since its empty position are left into the bottom row and it keeps onto the right of this ancestor, right? A heap then is a tree that meets the heap condition is also complete. Here's just one example of trees since the empty position are to the right of the ancestor. So this is a valid heap since each node is greater than any of its descendants. And the tree is also complete. While it does have some gaps in the bottom row, the gaps are limited to the very right of the tree, which is the right of the ancestor. So again, the parent needs to be greater than the children, and the missing should be at the very right of the tree. Heap properties. So while the heap condition dictates that the heap be ordered a certain way, this ordering is still useless when it comes to searching for a value within the heap. For example, let's say in the above heap, we want to search for the value 3. If we start at the root node of 100, should we search among its left or right descendants? Because we don't know the less than or greater than of the ancestor, unlike the binary search tree. So in binary search tree, we know that 3 must be among 100's left descendant. In a heap, however, all we know that is that 3 has to be a descendant of the 100 and can be its ancestor, but we have no idea as to which child node to search next. Indeed, the 3 happens to be among the 100's right descendant, but it could have also easily been among its left descendants. So because of this, heaps are said to be weakly ordered as compared to binary search tree. So it's weakly ordered. It's not as organized as binary search tree. While heaps have some order, as descendants cannot be greater than their ancestors, this isn't enough order to make heaps worth searching through. So since it's not as ordered, remember one of the key things with search, such as in binary search for ordered array, is that the data must be ordered for us to be able to search faster. So that's one of the key in life as well. If you want to search things faster, you need to be organized. You need to know where the location of each things. It needs to be easily remembered. It's the same with data structure. So the heap has two primary operations, inserting and deleting. So as we noted, searching within a heap would require us to inspect each node. So again, inserting therefore requires us to search each node, kind of like an ordered array as well. So search is not an operation usually implemented in the context of heap. So a heap can also have an optional read operation with which would simply look at the value of the root node. So the heap, so it also has a read operation, but it's only usually used if we're gonna start if we're gonna insert or delete something. Of course, we have to read the first or the root node, since that will be the basis of our search and insertion and deletion. So the heap has something called a last node. A heap's last node is the rightmost node in its bottom level. Next, let's go into the heap's primary operation. So there's another vocabulary in heap in which its last node. So here is the last node, since we know that this could have an empty position. So heap insertion. Let's see how far. Oh, we're almost done, basically. So to insert a new value into the heap, we perform the following algorithm. So we create a node containing the new value and insert it at the next available rightmost spot in the bottom level. Thus, this value becomes the heap's last node. So we create a node containing the new value and insert it at the next available rightmost spot in the bottom level. Thus, this value becomes the heap's last node. Next, we compare this new node with its parent node. So let's just back up a little bit. It's a trick. We create a node containing the new value and insert it at the rightmost spot in the bottom level. Again, rightmost spot of the ancestor at the bottom level. So that will serve as the front of our priority queue, or kind of like in ordered array priority queue in the last index. So thus this value becomes the heap's last node. So that's where the vocabulary last node is important. Next, we compare this new node with its parent node. If the new node is greater than its parent node, we swap the new node with the parent node because the parent needs to be greater, one of the properties of the heap. We repeat step 3, effectively moving the new node up through the heap until it has a parent whose value is greater than it. So let's see this algorithm in action. Here's what would happen if we are to insert a 40 into the heap. Step 1, we add the 40 as the heap's last node. So first, for insertion, actually, we need to trickle up 40, right? That's the step 1. Note that doing the following would have been incorrect here. Why? Because placing the 40 as a child of the 12 node makes the tree incomplete, since we've now had a node to the right of an empty positions. So again, since we now have a node to the right of an empty position, so in order for a heap to remain a heap, it must always be complete. Step 2, we compare the 40 with its parent node. Which happens to be the 8. Since 40 is greater than 8, we swap the two nodes. Step 3, we compare the 40 with its parent 25. Since 40 is greater than 25, we swap them. So step 4, we compare the 40 to its parent, which is the 100. Since 40 is smaller than 100, we're done. So the process of moving the new node up the heap is called trickling the node up through the heap. Sometimes it moves to the right and sometimes it moves up to the left, but it always moves up until it settles into the correct position. Sometimes it's move up to the left or move up to the right, but it always done so until it's not greater than its parent. Now, the efficiency of inserting into a heap is O log n. So once we insert that, it makes the notice that once we insert something, it makes it ordered again. Kind of like when we insert in an ordered array, we ship it to the right? So the efficiency of inserting into, however, the difference is that the efficiency of this heap array is O log n. As you saw the previous chapter, for n nodes in any binary tree, the tree is organized into about log n rows. So since at most we'd have to trickle the new value up to the top row, this will take log n steps at most.